Hello, Chemistry, Earth, Space Science. This is the beginning of the Unit 3, the dangerous compounds. This unit contains a lot of information revolving around using the periodic table and understanding more about how compounds are formed and how compounds are named and the formulas are written. So if we look at the various lessons in here, it's the periodic table is the first one. Then there'll be one on periodic trends, followed by one on valence electrons and electron configurations. Then ionic compounds, again talking about how they are made, how to name them, and how to write their formulas. Then covalent compounds, same thing, how they are created, how to name them, and how to write their formulas. And then finally, molecular geometry and polarity will come around full circle about the compounds. So this is lesson 1, periodic table and periodic trends. So the objectives for this lesson is to understand how the periodic table is created, why it's created the way it is. We're going to do through some direct instruction here. So I'm going to put these two videos online because they go along with a couple cute songs. So I'm going to get rid of that one. And here's another one that I'm going to share in class. I'm going to go ahead and link it separately in this video. It will be on the PowerPoint that's available for you to check, but it basically tells a lot about how Mendeleev came up with his version of the periodic table. So what's going on here? One of the things that happened early on, back in the 1700s, was we only knew about a handful of elements. Now I say we, I wasn't around. However, shortly after the 1800s, the number of elements discovered had quickly rose. And very often the way that they were organized was either by alphabetical order or maybe by their sizes, how heavy the elements were. So as the number of elements grew, we needed to find some way to organize them better. And Dmitry Mendeleev, a Russian chemist and teacher, was one to figure out a way to organize the periodic table better. What Mendeleev did in the 1860s was he was working on his textbook and using chemistry students, and then he said, let's look at how to describe the 63 elements that were known at that time and try to find a better way to organize them. So he came up with doing something that was pretty common that I think we do today. If you've ever had to check whether a deck of cards had all the cards in it, you could either count them out, see if there's 52 cards in there. But another way is to make sure that there's the ace through the king of every single suit. And the way you would do that, it was organize them into diamonds, then spades, hearts, and clubs, and then make them in a numerical order. That was a way to organize the cards that were in a deck of cards. So Dmitry Mendeleev did kind of the same thing, but what he did was he looked at the elements that were available at that time. And he made his own, quote, deck of cards. He took and put on every single card the name of the element and then some general properties about it that he knew about each one of those elements. He put them in order according to their masses. I said that was one of the two ways that they were organized. Put it according to the masses. And when he did that, he noticed something very interesting as he laid out his cards. He noticed that when he laid them out according to their masses, going from smallest to largest, began to show this odd little pattern. Essentially, the pattern was after every 8 elements, actually for Mendeleev it was only 7, there was a repeat of the chemical and physical properties. That cycle to go through from property, element, until it gets back to that same property, he called that a cycle. And he arranged the periodic table so that each row on his table represented a cycle, or as he's called it initially, a period. So if I look at this, I see that if I organize the elements that are in the second row on the periodic table, he saw that there's lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine in that order. And he saw that pattern repeat itself in that he saw that after number 7, it came back around and repeated the number of valence electrons, 1, 2, 3, 4, 5, 6, 7. Now, this is an oversimplification because honestly, in the 1860s, we were just learning a little bit more about the structure of the atom. So he wasn't necessarily looking at the valence electrons, he was looking at purely at their patterns, but just want to note that this is the pattern that he noticed. So he managed to take every single one of his columns and it represented a particular property. He wrote his periodic table. Now, it's not the most elegant thing, but he took his periodic table and he made the elements all go in a column that had the very similar properties. So if you look at a periodic table right now, you see lithium is right above sodium, is right above potassium, and all three of those elements are very reactive when they come in contact with water. So they'll have this very, very aggressive property where they essentially will catch fire if you put them in water. That's the first column on the periodic table, the column 1A. Now, Mendel's periodic table was a little different. If you look at this, it's not the most pleasant looking thing. He's got a few dashes in there. If you watch the video about Mendeleev that was earlier in this slide deck, he explains those dashes and why they're important. And actually, those dashes are super important to our understanding of the periodic table and actually giving Dmitry Mendeleev a lot of credit for what he discovered as far as the organization of the periodic table. So let's look at this in a writing that's a little clearer. So here's one version of the periodic table, one that Mendeleev may have been using. And you'll notice like the first row has just hydrogen, and the second row has lithium, beryllium, boron, and carbon. The third row has sodium, magnesium, aluminum, and silicon. The fourth row has potassium, calcium, and blank, and titanium. Well, the blanks on this little figure here represent the craziness of what Mendeleev did. He had the elements known to man at that time, and he said, essentially, this blank that's at number 44, he said, we haven't discovered an element yet, but we're going to, and I can tell you something about it. And he was able to predict a whole lot of really amazing properties of both 44, 68, and 72. Now, if you look at the periodic table, there's like this one was called Eka aluminum because it's just below aluminum, and this was called Eka silicon because it was just below silicon. So what did he do? He saw the periodic table and he says, I think I can make a chart that organizes this much better. I can make that table be arranged so that the columns represent a specific property and it will be repeated in cycles or in rows or periods on the periodic table. And what that's led us to do is expand our ability to take the periodic table and predict other elements. Now, if you look at the periodic table in our classroom, you notice there's a whole lot of man-made elements. We're going to talk about them in a second. What Mendeleev's genius was able to do was to be able to predict the properties of those elements that only exist for fractions of seconds. Quite amazing what he was able to do back in the 1800s. So let's take one of those examples. Mendeleev predicted element number 32, which had not been discovered yet. It was in the section that was 32 on the periodic table. And he said, I can give you some properties. And he predicted a bunch of properties of that element. And this is the one that is Eka silicon. So what he did was he looked at it and says, I think that whenever you find this element, number 32, it's going to have an atomic mass of 72. It's going to have a density around 5.5. It's going to have a valence number of 4, meaning it has 4 valence electrons. We'll talk a lot more about that in a unit to come, in a lesson to come. And he also said this should be kind of a darkish gray color, like a typical metal, but it's going to be darker than normal. And when the element germanium was discovered, number 32, it was pretty amazing because what he did was we discovered germanium, and lo and behold, the atomic mass of germanium, the predicted element that was going to fall in number 32, had an atomic mass of 72.6, has a density of about 5.3. It does have four valence electrons, and it was gray. It was actually lighter gray than Mendeleev predicted. This ability to predict properties of an element before they're discovered is the essence behind why Mendeleev was given credit for this organization of the periodic table. If you watch the video that I suggested you watch, and I may show in class, that shows how Mendeleev was not the only person trying to organize the table. As a matter of fact, other people were doing the same thing. However, Mendeleev was a smart one to say, wait a second, there are some elements we don't know yet. And the ones he got the most recognition for were these four: germanium, gallium, scandium, and technetium. These four elements were not known to Mendeleev, but because there were holes on the periodic table, he predicted their properties. He predicted what these elements would look like. And when he was accurate, he was given a lot more credit, because initially it's like he was just organizing the periodic table. It wasn't organizing the elements. They didn't give him a whole lot of credit for his success. But once he started predicting and messing with the periodic table, saying, no, I don't think it's like this, we need to skip a spot, his genius came out. So if we look at periodic table, it's not perfect. He's got a lot of weird things on there that were not ideal for his time. It was 1860, so cut the guy some slack. He was able to sort them because of their masses and skip over ones that were not there and try to predict them. He also noticed that if you organize them by atomic mass, there was another anomaly. If you look at them with atomic mass, iodine, because it's lighter than tellurium, was positioned in column 6, and tellurium was going to be in column 7. But when Mendeleev laid those cards out, he made another fascinating discovery. He said, wait a second, iodine doesn't look like the elements in column 6, and beryllium doesn't look like the elements in column 7. So what he proposed was switch the order, which again blew some people's minds, to say, wait a second, this whole table that we're looking at, everything is in order of increasing mass. You're going to tell me these two have to be switched. And yeah, they did, because when you look at the valence electrons and the electronic structure of these elements, iodine fits much, much better structurally in column 7, and tellurium fits much, much greater in column 6. There's his periodic table again, but here is ours now. So you get a copy of this periodic table. You're going to see this periodic table, this one. You've seen it time and time again. Every time we've had a quiz that needed something off the table, you're using this table. This is what's recognized and is accepted today. So we did this before briefly. I'm going to do it one more time. That if you look at the periodic table and you look at each one of those cells, suppose I grab the element sodium right here, and I take that sodium and I pull out the information off of that. The number that is at the top on our periodic table, it's in the middle of the cell. That's the atomic number. And you remember we said that was the number of protons. And then comes the symbol. Symbol is going to be a 1 or 2 letter designation. If it's 2 letters, the first one is capital, the second one is lowercase. There's only a handful that are one letter, and that's just because the early ones, it just had one. The name may be on there. It is on our periodic table. And then finally, the atomic mass is on there. And our atomic masses may look a little different than this. This is the very, very specific atomic mass, very, very similar to the one on the periodic table in our classroom. So if we look at the periodic table, and this will represent, this next slide will talk about the one that we have in our classroom, we'll notice something kind of interesting. On the one in our classroom, we have different colored fonts. We have red, we have black, we have blue, and then we have white. On On the one in our classroom, the ones that are red are over here on the right-hand side. On this one, it's these ones that are green. Those are all gases, okay? And then the ones that are on our periodic table in the classroom are these two that are in red. And those two are blue, and those are liquids. These two are liquids at standard conditions when we're talking about 1 atmosphere and 25 degrees Celsius. Bromine and mercury are both liquids. The blue ones, as you can see, the majority of the periodic table are blue. That means those are solid in their standard state. A lot of those, not all of them, but majority of those are metals. And then finally, the ones that are in white are the ones that are man-made, meaning they do not exist in nature. They were created purely in a cyclotron or some other device that allowed the fusion of nuclei to make a bigger and bigger atom. So let's break the table down one more time. So this is what we need. You need to know where on the periodic table are the solids, where are the liquids, where are the gases, also where are the man-mades. On our periodic table, they're clearly labeled, but they are black, red, blue, and white. Another thing about the periodic table, if you look at it, how it's organized, and again, this is after Mendeleev has put the table together, is if you start looking at other properties, like for instance, which ones are metals? I said most of those solids are metals. Matter of fact, mercury is a metal, and mercury is a liquid. So periodic table is organized also, and there's section of periodic table where there's metals, nonmetals, and metalloids. I guess we need to identify what a metal is. A metal is any element that in its elemental state is shiny. The fancy word for shiny is metallic luster. We've always seen metal like chrome or copper or titanium or aluminum. They're shiny. That shininess is called metallic luster. It means if you can buff it, rub it smooth, it will appear shiny. And all metals conduct electricity and heat. That's because of their structure and how their electrons are bound together. All of them are malleable. Malleable means that you can pound it with a hammer and it will dent rather than breaking into a bajillion pieces. It also means you can mold it into a shape. Last property of a metal is they are ductile, which means they can be drawn out into a wire. So all metals have all four of these properties. They are shiny, they conduct electricity and heat, they are malleable, and they are ductile. And as I already said, a majority of the periodic table is going to be metals. We'll see that periodic table in a second. If you flip that around to things that are not metals, which means they are not they're exactly opposite of metals, we call those non-metals. And non-metals are dull, they're not shiny. They're poor conductors of heat and electricity if they conduct at all. They are not malleable. The word that gets used for not malleable is brittle, meaning it will break up if you decide to hit it with a hammer or you drop it. It's going to break into a bunch of pieces. They're not ductile. You pull them and they're going to break rather than form a wire. And those are normally all on the right side of the periodic table. And again, I'm going to show you a periodic table in a second that has them all labeled out. So what about things that are kind of metals and kind of nonmetals? Well, those are called semi-metals or metalloids. Semi-metals and metalloids are the ones that have properties of both. So if you think in terms of the four properties that metals all have, metals have all four. Non-metals have none of them. But there are some elements that have only one of the properties, some that have two, and some that have three. So if they have one, two, or three of the properties of a metal, but not all four, they're considered to be a metalloid or a semi-metal. And those are located between the metals and the non-metals on a periodic table. And they actually have the elements of boron, silicon, germanium, arsenic, antimony, beryllium, and astatine are the semi-metals or metalloids. If we look at a periodic table, it's kind of interesting in that the metalloids make like this staircase from boron diagonally down to astatine. Now I have OG, the newest element on the periodic table, just labeled in pink because, again, we're talking about Mendeleev's periodic table. It's a matter of trends, and it's believed that that element, based on where it's located, is going to either fall under the non-metal stage or it might fall under the metalloid stage. Well, considering this goes in a diagonal, our prediction would be it's going to be if we had it for more than a couple of nanoseconds, it would be in a metalloid state. You also notice besides the diagonal, there's germanium and antimony right here are like offshoots of it, but it's a diagonal line. And notice, if you take that diagonal line and you go to the left of it, there's all those metals. Okay, if you go to the right of it, they're all the nonmetals. And yeah, hydrogen's way over here. You'll see a periodic table a little bit later that will put hydrogen here also right next to helium, which would make more sense for the way this is arranged. Okay, so we know which elements are solids, liquids, and gases and man-made. We know what elements are metals, nonmetals, and metalloids. The next way the periodic table is organized or is sorted is according to groups or families. Now, groups are numbers. Groups are numbers. It's a matter of there's two systems that were used. One, an older system that used the numbers 1A through 8A. I find that one to be the most useful. And a second system that's become more accepted as of late is one that just labels the columns 1 through 18, because on a periodic table on our wall we have 18 columns, so they just label them 1 through 18. So let's look at the element groups and how they're laid out. So here is a periodic table that has across the top the elements 1 through 18, or the columns 1 through 18. Now, what's the benefit of this? You can say, what's the element in the fourth period in the 14th column? Fourth period, right there, 14th column, that would be germanium. And you can identify the location of an element using those numbers. Now, that's great if you're trying to identify it, but one of the things the old system has that the new system does not is a connection with the structure of the elements. So here's the other system, like notice across the top, they're going to have little letter A's. So it's 1A, 2A, and then all these one in this little bunker here that's in the middle of the periodic table, they all have in it the letter B after it. So it's 3B, 4B, 5B, 6B, 7B. And yes, for some reason, I don't 100% understand the reasoning, but 8 is a really cool number within the periodic table. You'll see that when we get further into bonding. So they just made the next three columns all label them as 8B. Then they wrapped it back around, 1B, 2B, and that's basically so it becomes 1, 2, and then 3. 4A, 5A, 6A, 7A, 8A, and 7A and 8A. That's great. It's really cool. But here's the plus about this method, this particular periodic table. Those numbers that are A's represent the number of valence electrons. So when we were mentioning earlier that element number 32, germanium, had 4 valence electrons, that meant it was going to be in column 4A. And the periodic table is arranged according to numbers of valence electrons. Those we'll see in the next lesson, that's the elements that are responsible for bonding. So column 1 has 1 valence electron, 2 has 2, 3A has 3, 4A has 4, 5A has 5, 6A has 6, 7A has 7, and 8A has 8, except for helium, which only has a total of 2 electrons, so it only has 2 valence electrons. All this stuff in the middle, as well as this stuff on the bottom, they all have 2, because B is the second letter of the alphabet. So everything in the middle has 2 valence electrons. Now, keep that kind of in the back of your brain, because we're going to come back to that in talking about bonding and the structure of the atom in another lesson. Okay, so they have groups, and here's our periodic table. Why did I show you this? Well, notice the periodic table that I give you across each one of the columns has both numbers. They have the small number, the 1 through 18, and they also have the A and B numbers across the top. I did that when I created this periodic table because I want you to be able to use it in some way, shape, or form that will allow you to utilize the benefits of both number systems. You're not often going to see that on a manufactured periodic table. This is one that I put together to make it have the appearance that I wanted to have. Okay, next thing. On the periodic table, the instead of being aligned with groups, they're also aligned with what are called families. Now, families have names. Whereas a group has a number, a family has a name. And these names are all ones that are used a lot in chemistry. So let's look at the periodic table and how it breaks down. So on our periodic table, we have column 1, with the exception of hydrogen, which doesn't actually get put into a group at all. Column 1, that first column is referred to as the alkali metals. They all have the similar structure. They have the 1 valence electron. They all are very reactive with water. These are ones that are referred to as the alkali metals. One of the reasons why they're called alkali metals is when they react with water, they make the water basic or alkaline. Column 2, that's going to be 2A and 2, is the alkaline earth metals. Sounds very similar to the first column, but again, the naming is the alkaline earth metals. We jump over to the other side. Another really important column on the periodic table is column 8A. That column 8A is where the noble gases are. Those are the nobility of the periodic table. These are the ones that are ideal in their electronic structure. They have a full valence shell. They have a full valence shell. They are most stable of all the elements on the periodic table. The reason why they're called the inert gases is because they don't really react with anything else. They are inert. That means not able to react. Another column that's very popular in naming is the pink column here, 7A. That's the halogens. And then the other ones have names that are pretty close to what you would expect because they're almost all based on the first element in that column. So the oxygen family starts with O, the nitrogen family starts with N, the carbon family starts with C, the boron family starts with B. So those 4 columns are just labeled according to the family that is there. Also in the periodic table, these ones in the middle are referred to as the transition metals. They are the transition between this main part of the table and this main part of the table. So they're called the transition metals. And then these 2 rows at the bottom, they actually fit right here where this dark line is. The periodic table would be crazy, ridiculously big if we put those elements where they really are, which is right there. It'd be super, super wide. I'll show you in a little bit a image that shows that particular version of the periodic table. But they usually get put at the bottom for no other reason than we want the periodic table to be able to fit on an 8.5 by 11 sheet of paper. Let me show you that long version of the table. So here's what it really would look like on a normal scale, where that lawrencium, lanthanide, actinium rows are all in the right spot, which is down here after six in the 6th row. That's where they go, but the reality is it's really, really hard to put anything in these cells. So since it's hard to put anything in these cells, they tend to not show the periodic table this way. They show it the way we're used to seeing it, which is with those 2 really skinny rows that are over here. They get put on the bottom and makes it where there's more room in the cells to be able to put information we may need. Now, I do have to bring to your attention, there's 2 other names of the groups. The nitrogen family and oxygen family have an alternate name. And right here you see the nitrogen family is called the pictogens, Pnicogen, the pictogens. And the oxygen family, another one of the name for that is the chalogens, which is really annoying because it sounds so much like the halogens. Those are 2 very academically based terms, old school terms for those 2 groups, but you should be aware of those. Another thing as far as getting around the periodic table and getting your feet wet is that those two columns on the left-hand side and right-hand side are usually referred to as the main group elements. Those are the ones that are groups 1, 2, 13, 14, 15, 16, 17, and 18. Those are the main group. The transition elements are the ones that are in the middle. The lanthanide and actinide series are referred to as intertransition metals. There's also a section that gets a cool name called the post-transition elements, and those are the ones in columns 13, 14, and 15 that are below, lie right next to the transition metals. So let's take a look at that. So here we have that one. So main group elements those, main group element these. That's the main part of the periodic table. Transition, intertransition, and then these get another term used for them, which is the post-transition elements. Just recognizing that columns 1A and 2A, as well as column 3A, 4A, 5A, 6A, 7A, and 8A are the quote-unquote main parts, main group of the periodic table. Okay, next. I kind of gave this away earlier, but if you look at a periodic table, the rows are called periods. They're numbered 1 through 7, and I already told you where the lanthanide series goes and actinide series goes on the periodic table. If you look at your periodic table that I've been giving you, you'll notice along the left-hand edge are the numbers that represent the period. So the lanthanide series goes here, so they're part of the period 6 subset. Just a matter of where everything falls on our periodic table. And then one more image just to bring out the groupings. But here's another one with the metals, nonmetals, and the intertransition metals labeled. And the long version. Okay, so that completes this particular video on the periodic table. I'm going to in a little bit do another video on the periodic trends so that you can do that. But this is a rather long series of notes and a rather long PowerPoint, but hopefully you bear with me. Watch the video, take some notes, use the note sheets if need be, and prepare for being able to do stuff in class rather than listening to me in the classroom setting. You're going to be listening to me on these videos. So I will see you on the next video. Toodles.